What are time crystals? This term sounds about as unscientific as possible, more like something from the Marvel Cinematic Universe. Nevertheless, it is a fully scientific concept that even has real practical applications, for now mostly theoretical, but the further research goes, the closer this technology gets to practical implementation. And that practical implementation has come a little closer. Scientists have, for the first time, managed to create a real-time crystal whose unique properties are visible to the naked eye. The method of its fabrication was published in an article by Ivan Smolyuk and Hanqin Zhao in the journal Nature in September 2025. As you may have already guessed, in our video today we will talk about what time crystals are, how they work, or rather how they might work, and what benefits we may hope to extract from this technology. Here is the idea. A conventional crystal has a specific spatial structure. When moving through the crystal, we will find the same geometric shapes that repeat after a certain distance. That is, we can select within the crystal a certain region, also called a unit cell of the crystal lattice, move some distance away, and in a region of the same size, observe exactly the same ordering of atoms. A time crystal is the same thing, but the ordering changes not with distance but with time. The arrangement of atoms in the crystal changes, but not randomly. Instead, after equal intervals of time, the atoms once again appear in the exact same configuration. Essentially, the same thing is observed in any oscillating system. And indeed, if we look at a mathematical pendulum, its bob truly ends up in the same state after each interval of time equal to the period of oscillation. However, this happens only in an idealized case. In a real pendulum, meaning an actual weight on a string, the energy of the oscillating system constantly decreases due to friction, air resistance, and similar effects. Therefore, for example, the speed of the bob at some point even after a single period of oscillation will already be a little smaller than one period earlier. Moreover, the independence of oscillation frequency from amplitude is also a known idealization. In reality, there is a dependence, though weak, and at small amplitudes it can be neglected. However, it still exists, and as the pendulum loses energy during oscillation and the amplitude decreases, the oscillation frequency slightly decreases. Therefore, a real pendulum is not a time crystal, because strictly speaking, it does not reproduce its states exactly. But what if we somehow compensate for the loss of energy? In general, this is possible. For example, a string played with a bow produces an approximately constant sound, meaning it oscillates in a stable manner. Another example is a quartz resonator like the ones used in quartz watches. A tiny tuning fork made of quartz inside them oscillates under the influence of an electric field created according to an electrical signal that the quartz itself produces when oscillating. In both of these cases, a non-periodic external influence, the motion of the bow or the operation of a battery, supplies the system with energy and maintains stable oscillations. Such systems are called self-oscillating systems. And although self-oscillations are stable, this still is not a time crystal. The stability is achieved due to external energy input. We are, roughly speaking, forcing the system to periodically return to repeating states. In our analogy with an ordinary spatial crystal, this would be similar to manually placing atoms in order to achieve crystalline arrangement. The beauty of crystals lies in the fact that we do not need to do that. They arrange themselves this way because such periodic arrangement is optimal from the point of view of interactions between the atoms, or ions, of the crystal. A time crystal must be the same. It should oscillate not because someone pushes or drives it, but on its own, due to its internal structure and the nature of the bonds between its elements. It can be explained another way. Both the pendulum and the string and the quartz plate oscillate because we have imparted some energy to them and maintain them in a state with that energy. In a time crystal, periodic changes of state, that is, oscillations, must occur without any energy, or more precisely, when the system is in a state with the lowest possible energy, as physicists say, the ground state. If this is achieved, then such oscillations could be maintained for however long without any intervention from us. If you just thought that this entire concept suspiciously smells like perpetual motion, then you are, generally speaking, right. Nevertheless, in 2012 Nobel laureate Frank Wilczek published a paper in which he suggested that such a thing might be possible. In it, he relied on certain nuances of the mathematical description of quantum mechanical systems. By the way, we covered these in a separate video, and understanding what we will talk about next will be easier if you watch it, although I will try to explain things so that they are clear even without that. So, in quantum mechanics, the characteristic of the state of an object is the wave function, a quantity whose square gives us the probability of detecting the object at a given point in space during measurement. This function depends on coordinates and, generally speaking, on time, and it must also be a solution of the Schrödinger equation, which is fundamental for quantum mechanics and must be satisfied by all actually existing quantum mechanical systems. And it turns out that for stationary states, meaning states in which all observable parameters of the system do not depend on time, wave functions satisfying the Schrödinger equation must have a general form of the following type. The phi of x term is the so-called spatial part of the wave function, while time appears only in the exponent, where the energy of the system is also present, including its energy in the ground state, where this energy has the lowest possible value. But wait a moment, my viewers may object. You have just said that we are searching for a stationary solution independent of time, and yet in the exponent you have time. The wave function really does depend on time. However, this does not yet mean that any observable parameters of the object described by this function will depend on time. Indeed, let us take such an observable parameter as the probability of detecting a particle at some point in space with coordinate x. To obtain it, we must square the wave function. At the same time, we must remember that we are dealing with functions that yield results in complex numbers, and in order to square a complex number, it must be multiplied not by itself, but by the complex conjugate, in which the real part remains unchanged, and the imaginary part has the opposite sign. In our case, the complex conjugate of our wave function will look in a corresponding form, and when squaring, the product of the time-dependent exponentials will always give us 1. The probability of detecting a particle at a given point in space will be determined only by the spatial part of the wave function and will not depend on time. In the terminology of classical mechanics, this would mean that the particle is motionless. That is, our solution indeed is stationary from the point of view of observable parameters of the object. However, internally, at the level of the wave function, the dependence on time exists. Moreover, it turns out to be oscillatory. Indeed, according to Euler's formula, a complex exponential is equal to an expression whose real and imaginary components oscillate according to cosine or sine laws. Meaning that, although the observable parameters of the object described by this wave function will be constant and will not change over time, at the quantum level, the wave function will always undergo oscillations, including when it is in the state with the lowest possible energy, that is, in the ground state. This was the core of Wilczek's idea. What if there exists a way to construct a quantum mechanical system such that these quantum oscillations of the wave function exert some influence on the real observable parameters of the system? If we could learn to do this, we would obtain a perfect time crystal, oscillating even without any energy being pumped into it. Wilczek was fascinated by this concept primarily because of its elegant absurdity and by how time crystals would push the boundaries of our understanding of what is possible and impossible in our universe. However, after the publication of his work, proposals began to appear suggesting what useful applications could be found for time crystals if they could be created. The most obvious idea was to use time crystals for measuring time, as well as precise frequency generators, which are necessary in electronics and radio engineering. Later, the idea arose to apply them in various sensors, and later still, the thought appeared to create new types of computer memory based on them. If we combine two time crystals in such a way that they oscillate in antiphase, then their oscillations will cancel each other, and at the output we will obtain the absence of oscillations. Let the digit 0 be recorded in our memory cell in this state. And conversely, if the crystals oscillate in phase so that their oscillations reinforce each other, then we will obtain the digit 1. In general, Wilczek's idea turned out to be highly intriguing, and journalists particularly liked it, being charmed by the very term time crystals. However, in 2014, Only 2 years after the appearance of Wilczek's original work, predicting the possibility of time crystals, Japanese physicists Watanabe and Oshikawa published a study in which they demonstrated that time crystals in the form predicted by Wilczek are impossible, or more precisely, that it is impossible to realize observable oscillations in a system located in the ground state without changing its energy. And it seemed that the question was closed. But after yet another year, in 2015, Polish physicist Krzysztof Sacha proposed a way to bypass the prohibition and create, if not true time crystals as Wilczek imagined them, then something very similar. Sacha's key idea was the following. If we subject a system to some external periodic influence, then, under certain circumstances, oscillations may arise in it with frequencies different from the frequency of the external influence and determined solely by the properties of the system itself. These oscillations may also be sufficiently stable and independent of the strength, frequency, and other parameters of the external excitation within certain fairly wide limits, practically like Wilczek's time crystals, with the only difference being that they will not occur entirely by themselves. The system will require external excitation, although its response to this excitation does not have to directly correspond to it. Such objects were named discrete time crystals. Already in 2016, Sacha's ideas received practical implementation. A team of scientists, led by Christopher Monroe from the University of Maryland, created the first discrete time crystal from a chain of ytterbium atoms cooled to ultra-low temperatures. I will illustrate the principles of operation of discrete time crystals using a simpler example, time crystals based on doped semiconductors. First realized in 2024, in a joint study by scientists from the Paul Drude Institute in Berlin and the Atomic Center Bariloche in Argentina. My explanation of the physics behind their time crystal will be very strongly simplified, but I hope that at least the general essence will be conveyed correctly. The basis for creating the crystal is an N-type doped semiconductor, in which atoms with a greater number of valence electrons than the main lattice atoms are incorporated into the crystal lattice. For silicon, this may be, for example, phosphorus. 4 electrons of phosphorus participate in forming interatomic bonds in the lattice, and the 5th ends up in a quasi-free state. Then, the semiconductor is placed in an external magnetic field. An electron possesses spin and magnetic moment, meaning it is a tiny magnet. In an external magnetic field, this electron may occupy 2 possible orientations, such that its spin is directed in the same direction as the magnetic field, or in the opposite direction. In this case, the first state will be more energetically favorable, and all or almost all electrons of the crystal will occupy precisely it. Let the initial moment in time be such that our electron is oriented in the most energetically favorable way along the field. If now we apply to the sample a short microwave pulse of the required frequency, the alternating magnetic field of this pulse will rotate the electron's spin. With correctly chosen amplitude and duration of the pulse, the spin can be rotated almost by 180 degrees, switching it into the antiparallel state. In the absence of further influence, the electron will remain in this state for quite a long time. But if we immediately apply a second identical pulse, it will again rotate the spin approximately by 180 degrees, returning it to the parallel state. Thus, if identical microwave pulses are applied with a period t, then the spin will alternate between 2 positions, up, down, and so on. But this is in the idealized case. In reality, we are not always able to set the pulse energy exactly so that the spins are turned precisely by 180 degrees. For example, we may obtain slightly under-rotated atoms or slightly over-rotated ones. The following pulses will only increase the number of errors, which will accumulate, and over time, the system will cease to produce the response to the pulses that we expect. A completely different situation arises in a crystal where electrons interact not only with the external field, but also with the fields of their atoms, as well as with the fields of other electrons. The situation becomes even more chaotic, but paradoxically, it is precisely from this chaos that a certain order emerges. The first pulse will also rotate the spins of the atoms into the opposite direction. But due to the noise existing in the crystal, it will rotate them differently. The total magnetization of the material after the flip will not become equal to -m, but will equal, let us say, -0.7 m, meaning that the total change in magnetization will amount to 1.7 m. Then, after the first pulse, and in the interval between the first and second pulses, the external magnetic field will attempt to return the electron spins to their initial orientation. And it will do this differently for different electrons. The system will become even more chaotic. The second pulse will rotate the spins as it should, by 180 degrees. By this moment, the spins are already oriented in space rather chaotically. So a rotation by 180 degrees, leading to a change in the sign of magnetization, will change it from minus 0.3 m to 0.3 m, meaning it will change by 0.6 rather than by 2, significantly weaker than after the first pulse. After the second pulse, the internal magnetic fields of the crystal will again attempt to rotate the spins, but now in the opposite direction. Simply put, the internal fields of the system, which introduced chaos into it after the first pulse, will now act in the opposite direction, removing this chaos and ordering the system. As a result, by the moment of the third pulse, it will return almost to the same state in which it was before the first pulse, and therefore the third pulse will also carry out an almost correct flip of the system with a change of magnetization of 1.7 m. From the point of view of an observer, the crystal will begin to respond differently to even and odd pulses. Odd pulses will cause a strong magnetic response, and even ones, only a comparatively weak signal. And if the period of the incoming pulses is equal to t, then the spin oscillations in the crystal and the oscillations of magnetization caused by them will occur with a period of 2t, twice as long and with twice smaller frequency. This, of course, does not look too similar to the time crystal described in Wilczek's original work. The oscillations do not occur by themselves, but are caused by an external pulse, and moreover, their frequency is strictly determined by the frequency of the external pulse. However, this is also not merely forced oscillation, where an external force drives the system in one way or another. Here, something much more interesting happens. The system transitions from order to chaos and back to order. And although these transitions occur in accordance with the periodicity of the external microwave pulse, they turn out to be only weakly dependent on the pulse parameters themselves, such as intensity, duration, and the like. The final intermediate orientation of the spins will depend on the character of the pulse. However, by changing these parameters, we will simply create different varieties of chaos. Yet the very nature of the transition order-chaos order will remain unchanged. And it is precisely this that allows scientists to call such systems time crystals. And with the help of such systems, it is indeed possible to implement a number of interesting technologies. For example, memory resistant to external disturbances for conventional or quantum computers. A memory cell of this type may consist of two such crystals driven by the same microwave pulse. Let us assume that we consider the digit 0 to be written into the cell if a strong magnetic response, the transition from order to chaos, is produced by them simultaneously. And if the crystals respond to pulses out of sync, then we may consider that the digit 1 is written into the cell. Writing information into such a cell can be done fairly simply by sending an extra pulse into one of the crystals, which will reprogram its behavior. Such a system will turn out to be not only weakly sensitive to the parameters of the reference pulse, such as the intensity or frequency of the microwave radiation, but even to the frequency at which such pulses are applied, since both cells will undergo transitions synchronously, and their mutual state, which defines the information written into the cell, will be preserved even if the periodicity of the reference pulse fluctuates. Therefore, modern research in the field of time crystals is aimed not so much at creating an ideal time crystal, as close as possible to Wilczek's idea, but rather at learning to create the highest quality discrete time crystals like the ones we have described above. There are also those who are thinking about creating time crystals closer to Wilczek's ideal, and among them are Ivan Smolyuk and Hanqin Zhao, whose work we mentioned at the beginning of our video today. The main element of their time crystal is the so-called nematic liquid crystals, special liquids whose molecules have a long, elongated shape. Because of this, they tend to preserve orientation in space, to be turned in the same direction. It is this shared spatial orientation that makes these substances similar to crystals, whereas the fact that the molecules can move in space fairly freely makes them similar to liquids. An important property of liquid crystals is that they transmit light of different polarization differently. It is precisely this property that allows liquid crystals to be used in different optical devices, for example, liquid crystal displays, and we have a separate video about how this works. But let us return to the setup of Smolyuk and Zhao. In it, a thin layer of liquid crystal was placed between two glass plates. On the lower plate, micro scratches are made in a certain direction, and the molecules of the liquid crystal contacting this surface reliably orient themselves along these scratches. This orientation is fixed and practically does not change. The upper plate, however, is coated with a layer of special photosensitive dye. The molecules of the dye, under the action of light, constantly perform small random twitches, sometimes turning slightly clockwise, sometimes a little counterclockwise, and so on. For different molecules, these twitches occur differently, some a little faster, some a little slower, some stronger, some weaker. This chaos is transferred to the liquid crystal. The molecules located directly at the surface attempt to align slightly with the current average direction of the dye. The molecules slightly below attempt to align with the upper layer, but slightly more weakly. The result is something like a decaying chain of rotations extending into the depth of the liquid crystal. As a result, the entire thickness of the liquid crystal finds itself between two competing influences. Above, the chaotically drifting orientation of the photodye, and below, the rigidly fixed orientation. In addition, neighboring molecules of the liquid crystal influence one another, attempting to make adjacent molecules move in coordination with them. This leads to the chaotic twitching above transforming not merely into noise, but into complex organized waves of reorientation that propagate through the layer of the liquid crystal. From chaos, order emerges. Stable moving displacement waves appear, which have periodic character both in space and in time. And the repetition of configuration in time, that is what a time crystal is. Since a liquid crystal transmits light of different polarization differently, these waves become visible if one looks at the crystal through a polarizing lens that transmits only light of a certain polarization. Where the layer of crystals is oriented in the direction of the lens, there will be a bright stripe, and where it is perpendicular, a dark one. The Smolyuk-Zhao time crystals are significantly closer to Wilczek's original concept. Here too, there is energy pumping into the crystal in the form of external illumination. But these are not periodic kicks that impose pulsations of magnetization as in our previous example. More precisely, any electromagnetic disturbance is already periodic pulsation, yet no additional periodicity needs to be imposed here. And moreover, as far as I understood from the original work, the parameters of the time crystal do not depend rigidly on the parameters of illumination. It is sufficient only that the light be bright enough to cause displacement of molecules in the dye layer, meaning that the periodic properties arise within the crystal itself and are only weakly connected to the external excitation. It merely needs to exist, supplying energy to the crystal. Unfortunately, the Smolyuk-Zhao time crystals have an important difference from Wilczek's crystals. They are macroscopic, not quantum objects, obeying the laws of classical hydrodynamics, thermodynamics, and electrodynamics, and not possessing quantum mechanical properties. And therefore, they are not suitable for the same quantum memory, for example, nor for many other things for which true quantum time crystals are expected to be used. However, thanks to this work, we have taken yet another step toward Wilczek's idea. We have already had for quite a long time the imperfect, discrete quantum time crystals, and now we have the good, but classical time crystals. Who knows, perhaps with time we will learn to combine the advantages of both approaches and create good quantum time crystals. Time will tell. However, macroscopic time crystals may also have practical applications of their own. For example, Smolyuk and Zhao themselves write that they can be used as new means of protection against counterfeiting of money and documents. Security elements based on liquid time crystals will display a dynamic periodic pattern whose character will depend on such parameters as the thickness of the layer, the composition of the liquid crystal and dye, and so on. In addition, time crystals based on liquid crystals can be used to modulate light signals in general, which may find application in the creation of lasers, radio communication, and also photonics, a new promising direction in computing technology in which flows of photons will be used to transmit signals just as in electronics flows of electrons are used, only better, faster, and with lower energy consumption. By the way, I am already preparing material about photonics, and perhaps I will mention there what application time liquid crystals may find in that technology. So, if this topic seemed interesting to you, subscribe to the channel to be sure not to miss the next episode. And if you enjoy our channel, then I ask you to support its work by becoming a sponsor. The link to the latter, and also the corresponding QR code, should now appear on your screens. And that is all for today. I wish all the best to you, dear friends, and until our next meeting in our future videos.